All right, in the last video, we took a look at what happened to the electric potential as we moved around increasingly complex circuits. Now, let's do something similar, except this time we're going to look at the current. Now, one of the things that I want to bring up is this. In the last one, this time I'm actually going to be using some light bulbs instead. So I've got light bulbs in here. They're going to act pretty similar to resistors. For our purposes, we're going to treat them exactly like they are resistors. So real quick, I'm going to switch this back over to voltmeter, and that's what we looked at before. So for instance, if I put it across the battery, I get 2.98 volts. And if I check the potential across this light bulb, we end up with about the same 2.98 when I get good connection on there. So we had loop rule where the potentials around a closed loop would have to, or the potential differences would have to add up to zero, where batteries give energy and resistors or light bulbs will take that energy away so that they can turn it into heat for a regular resistor. That's where the energy goes, or light and, as a byproduct, some heat, the way that these Edison bulbs work. So give energy, take energy away. Now, that's one way of looking at it with our potentials, and we're going to look at this a bit closer when we start analyzing big circuits, that while they're related to energy, they're not exactly the energy itself, and that's why we would have maybe 3 coming out of the battery, but we would have more than 3, depending on which loop we would look at, but each individual loop would only be 3. Now, that being said, the main reason that I started off with that is to draw some comparisons. For the voltmeter, to measure the potential difference, we put one side here and one side here. We always put things, the voltmeter, in parallel. I'm going to have a subsequent video that talks about how to use meters and how to set them up properly. But just as a heads up on that. Now, for us to take a look at what we want to look at now, which is going to be the current, we're going to look at the current going through each of the parts of our circuit and the total circuit, depending on the setup. We have to use something called an ammeter. So it measures amperes. Now, I've got the DMM, which I can adjust it to measure whatever I'd like, potential differences or amps or even some resistances. I can measure those directly with this. I'm going to set it aside for now. But to get us more used to it, I've got some snap circuit. These are actually a couple different meters. There's one switch setting that puts it to 5 volts, so I could use this as a voltmeter by putting it in parallel. And I've got a little over 3.5 volts is what it's measuring. That's one thing that we want to talk about. While we are going to use these to get a pretty good idea, the snap circuit equipment is not nearly as precise as a good like DMM. So a lot of times we'll use those in class. I've also got some other ones like this. This is an ammeter. We might use these in class too because I've got a number of these. But what I like about what we've got with these is they're going to snap right into the circuit and allow us to easily see what's going on. Now, tying back into what I said just a moment ago, we measured the different potential differences, or the voltages, if you'd prefer. A voltmeter must be connected in parallel, where one point is here and one point is here, and it measures the effective height difference between these two. Batteries are going to raise it up by 3 in this case, and then this one light bulb will lower it back down. And we're going to take a look at that in the next video. For an ammeter, it counts the current. And for us to count the current, I want you to think back to the introduction that I did. I described current as looking out the window and counting cars as they would drive past. Well, in order to get an accurate count, you have to have all of the current that you want to measure go through this meter, which means while the voltmeter is connected in parallel, the ammeter must be connected in series. So you'll notice that I've actually removed all of the wires like we had before with the voltmeter, and instead I am now going to hook this up with the ammeters themselves. I'm going to set these to amp, because they need to be set to amp. These have adjustable settings. I can do volts, which are a little off, a scale of 1 milliamp, and then a scale of 1 amp. Much in the same way that I can change the dial on my meter. So I'm going to connect the circuit here with these ammeters. Now, the ammeters do not have, or should not have, a noticeable resistance, so they should not change the circuit, although in real life they'll have a little bit of resistance, and they may change it slightly. Now, the main reason that I want to set this up is we can see the circuit is complete, our light bulb is on. That's one of the reasons why I've switched to the light bulbs, so that you can see when they're on and when they are not. All right, so here we go. On this side, I'm measuring what's coming out of the battery. Let's see, going into the light bulb. My indicator is at, I gotta remember I'm on the amp, so this is just under 1 amp. So it's saying that coming out of the battery, right through here, is about 1 amp, and that is going into the light bulb here, carrying energy into the light bulb. And then we measure what's coming out the other side, and we see that this one is also saying about 1 amp. Now, you may not be able to see that too clearly. I try and keep the resolution high enough, but I'm not certain it's going to carry over in this video. But that's what we're going to take a look at. So we've got one here that's measuring about 1 amp, and one here that's about 1 amp. This one might be a little under 1 amp, this one's a little over 1 amp, but that's because my meters, these are not as nice as I'd like them to be. I'm going to break the circuit here. Biggest thing that I want to point out is this. We have the current coming out of the battery, it goes into this resistor or this light bulb, and the same amount comes out the other side. One of the big things that a lot of people make mistakes on is they think that the charges are somehow used up in the light or the resistor or whatever other component. They're not. We're going to talk about that more when we start deconstructing this. That being said, let's see with a more complex circuit. So I'm going to take this, I'm going to put it here. So here's our battery. Let's see, I'm going to set this one here. And then I'm going to finally complete the circuit with one more right over here. And we can see the light bulbs come on dimly. They're not as bright as the one by itself. We'll talk about why in some of the subsequent videos. But now that we've got 2 of the light bulbs, that means that there's more resistance for this same battery, which means we get less current. All right, speaking of which, on the last one, we found that it was about 1 amp. This time, this one is reading about 0.5 amp. This one is also reading 0.5 amp. And this one's reading just a little bit above 0.5 amp, but that's because these meters could be a little bit better. In fact, let's try switching this one out with maybe the other one here. This one's right at about 0.5 amp. Great. They're all reading the same thing. What's happening is we have some charges, some current that's making its way through the circuit. We've got going through this point here. It's like looking out the window and counting the cars that go by at this point. We've got about 0.5 amps, so maybe about 50 cars. However many are going through here, we get the same thing here. You can imagine that this is like traffic driving around in a circle. All the cars are going through. We've got just as many here as here as here if we're watching at a given time. Now, the important thing about that is charges are not used up in a circuit. We're not removing any charges. In fact, the reason the charges are important is because them moving through the circuit causes energy to be released. As the electric fields act on them, a force is applied, and as they move, that's applied over a displacement. That's work. That's releasing energy that can then be used by, say, light bulbs or by resistors. The charges themselves, however, are not energy. They're only carrying the energy. All right, so let's take a look at a much more complex one because that's what we want to get to. Thus far, we've seen that with a simple circuit, we've got the current that's coming out of the battery is the same that is going into our resistor or light bulb, and it's the same coming out of the resistor or light bulb and going into the far end of the battery. We saw the same thing here, even with 2 light bulbs, 2 resistors, the current coming out was the same through this one, and back into the battery. So let's see what happens when we have a more complex circuit. So here we go. I'm going to put one here. I'm going to put one here. So this will measure the amount of current that is effectively coming out of the battery, going into this resistor, and coming out of this resistor. And we're going to have it come over here. And if you'll notice, we've got a split here. I have a parallel circuit. So this light bulb is in series with these 2, but these 2 are in parallel with one another. So here we go. I'm going to connect this. Oh, that's right. This one won't quite snap into place with the space that I have there. So here's what I'm going to do. I can hook that up. Yeah, there we go. So that's good. And then I need another one like this, or is it like this? Yeah, no. If you hook these up backwards, the needle will try and move the other way. That makes it really hard to see. Now, this is a preview of things to come. First off, you may be thinking that there's something wrong with my circuit. This light bulb is on, but neither of these appear to be on. If I remove this, however, this one gets dimmer and this one gets brighter. What you're not seeing right now, mainly because I'm going to need more power than I've currently got, is this one is on, and both of these are on. They're just not getting enough power to actually light up. We need a minimum amount of power for us to even be able to see the light bulb. So for instance, if I were to take this and unscrew this light bulb, we see that this one gets dimmer and this one gets brighter. When I let the current split, which is what we're going to see here, and go through the two of them, we end up changing the circuit. And this is something that I've mentioned before. If you change one part of the circuit, you can change everything about the circuit. In fact, let's look at our meters. So when I've got everything connected, while it looks like these two are out and broken, they're actually having current go through them. They have to, because this one is getting power, which only happens if you have a complete circuit. If I break the circuit, nothing gets power. So we do know that we have power going through, or current going through both of these, but they're not getting enough energy to light up. This one's very bright. If I take this one away, this one gets dimmer and that one gets brighter. Or if I take this one away, this one gets dimmer and that one gets brighter. Both of these actually have current going through them. They're not broken. We're just not getting enough power to them to see them light up. They're not getting enough energy to do their job. The important thing is this. Now that we've got a more complex one, I can see the following. Coming out of the battery, we've got just under 1 amp. It looks like it's maybe about 0.8 amp. I come over to here. On the far side of this battery, I've got maybe about 0.9 amp. These two should be saying the same thing. Again, my meters aren't quite perfect. But the important thing is this. Now we have the current going over here, and it's splitting off into these two. Through this one, I've got about 0.45-ish amp. It's a little bit under 0.5 amp. And over here, I've got the same, 0.5 amp, just a little bit underneath that. So we've got about 0.9 coming out of the battery. We've got about 0.9 coming through the far end of this resistor. So all the charges that are coming out of the battery are going, all of them, through this first resistor, because there's nowhere else to go. And so over here, they're going to end up splitting, however. Some of them go this way and some of them go this way. And because they split up, and they're the ones carrying the energy, not enough energy is getting to this one and not enough energy is getting to this one. There's energy getting to them, but not enough to get them to light up. And then the charges come through here. We can see on the far side of this that we've got about 0.5 amp of current going through this, and we've got 0.5 amp going through this one. If I take one of them away, so watch this. I'm going to take this away. We see that this one gets dimmer and this one gets brighter. That's because now we are no longer splitting the charges. Everything that goes through this one must now go through this one. That's why they're about the same brightness. And let's check what happened to our currents. Right now we've got about 0.5 amp. So now the total current coming out of the battery has been cut in half. 0.5 amp here. Coming out of the battery here, we've got about 0.5 amp. And then we come over here, we see coming on the far side of this resistor, what's coming out of it is about 0.5 amp. So when I put these back in, we get it to return to what it was before. We've got about 1 amp coming out, 1 amp coming out. We've got 0.5 amp through here, 0.5 amp through here. We're discovering something about our charges. We have a set amount of charges that are all moving through the circuit at the same time. Now, all of them have to go through this path, and all of them must therefore go through this resistor, because it's the only way to get from one side of the battery to the other. Charges are always trying to get from one side to the other. Now, one of the things that I want to point out on this is that the order on this doesn't matter. I could rebuild this with the two of them in parallel over here and the other one over there. In fact, let's try and do that real quick. So here's what I'm going to do. All right, so I'm going to leave my battery here. I'm going to make it where the split happens first. So I'm going to take this. I'm going to put these two in parallel with one another. And then, let's see. Then they connect with this one. And then, let's see. No, we'll go ahead and leave that there so it's clearer to see. All right. How do I want to do this? I can do this, and then I could do this. Oh, wait, we want to have it set up where we can put the ammeter there too. So let's go back to what I had originally. I should find some of the little 1 dots by themselves so I don't have to do this. Okay, in case, because this is a common thing that I run into, many students think that originally we had the one light bulb by itself that all the charges had to go through, and then they would split off. Order on these does not matter. In fact, I'm going to demonstrate that by putting these into place. Let's see, so this one will go here. We've got the 2 of them on, like we had seen before. And now, let's see. Oh, I've got to get this connected in a strange way. I could have planned this out a little bit better. All right, let's see. Let me grab one of my jumpers. Come here, jumper. All right. So, hopefully I'll get this hooked up right. What I need is from here. This? Oh, yeah. What I actually need is this. There we go. I know it can kind of be hard to see. Oh, I've got this ammeter in backwards. There we go. All right. Batteries are in the exact same setup. I used to have this one right over here on this side of the battery. I want you to notice that this does the exact same thing. It does not matter which side of the battery these things are on, because for anything to move, all of it has to move together. All right, so I've got this set up, and oh, I think I keep reversing this. Okay. Gotta be careful not to let those 2 touch, because I'm shorting the circuit if I do that. All right, this one reads about 0.5 amp. This one reads about 0.5 amp. That means 0.5 amp is going in here, and 0.5 amp, when I connect this, is going around through this path. Same thing that we saw last time. In fact, exact same numbers. And over here, we've got 1 total amp coming out here and going back into the battery. I technically need 1 other point where I connect all of these and see what we've got. See if I can do that. I'm going to do this in a strange way. This isn't my favorite thing to do, but it'll work. There we go. Okay. 0.5 amp here, 0.5 amp here. So we've got 0.5 amp going this way out of the battery and 0.5 amp going this way out of the battery. They meet up here. This one reads 1 amp, the combination of the 2 of them. So the charges are flowing into here, through here. And we have on the far side of this resistor, this light bulb, 1 amp coming over to the other end of the battery. So what we're seeing here is we have a set amount of charges that can actually move, and whenever they meet a junction, is the term that we're going to use, but a place where they could split off, they're going to split up in different ways. Now, in our case, we saw half of them go this way and half of them go this way. There's a reason for that, because both of these have pretty much the same resistance. Let's take a look at this in one more circuit, one with some of the resistors like we've worked with before. All right. Oh, actually, these might not be set for the resistors. That's okay. We're going to do this in a slightly more complex way, and I'm going to eliminate these sensors because they do a decent enough job, but they're a little bit off. They could be a better precision than what we've got. Knocked off one of the big pieces. That's okay. All right, here's what we're going to do. I'm going to take, and I'm going to put battery pack here. And what I'm going to need to do throughout this is I'm going to need to change where the circuit is connected because we're going to use our DMM, our good meter, right here. So give me just a moment while I get this set up. I believe I had the 5,100 ohm right here. So this is pretty similar to one of the circuits that we checked with loop rule just a little while ago. I'm going to use one of my jumpers as a cheat so that I can actually complete this circuit quickly and easily. And here we go. I'm going to do that. And one of the downsides is In fact, let's go ahead and check that. I may regret this. It should be fine. Yeah, that's having a 100 ohm. Is this going to light up? It is not. I wanted to show you all that it's complete and that it's lighting up. Let's see. Do I have an LED in here? I think I do. Hey, LED. Forward, this needs to be the positive side. Let's see if this is going to light up and hopefully not burn out. There we go. That way you have an indication that this circuit is on. This one's kind of an interesting one. It's not a regular light bulb. That being said, it's going to give us some feedback letting us know that the circuit is complete and everything's good to go. All right, we have some charges technically coming out of this side of the battery because this is the positive side. We treat it as a positive set of charges going through the circuit. So here's what I'm going to do. I'm going to draw this out real quick. All right, so we've got our battery over here. And it comes down over to a branch here that splits into 3 branches. One here, and one here with 2 resistors. Not my best drawing ever, but it'll do well enough. I'm going to go ahead and draw this thing in. This is a diode. We do not need to worry about those for the purposes of our class. It will have an effect on the circuit, but it's not going to have a huge one. It's going to have a potential drop, but we're only looking at the currents right now. All right, this is a 1,000 ohm resistor. This one is a 100 ohm resistor. This is a 100, and this is a 5,100 ohm resistor. All right, here's what we're going to do. I'm going to start breaking the circuit at different points. Now, I think we're going to be under 200 milliamp. Let's go ahead and check because I don't want to blow out the fuse on this. I'm going to break the circuit. The light is off. Remember, for the ammeter to work, it must be connected in series. So I'm going to have to break parts of our circuit so I can insert my ammeter into it. We can see the green light's on, so I've completed the circuit. It looks like it's less than 10 milliamps. So I'm going to switch it over to my 20 milliamp setting here, which is fine. All right. I'm getting a measurement here coming out of the battery, going into the circuit is about 6.7 milliamp. So my current right here is equal to 6.7 milliamp. Everything that we measure is going to be in milliamp for this one. Okay, now I need to find the current. Some of it is going to go through this branch, some of it's going to go through this branch, and some of it's going to go through this branch. And hopefully they're all going to meet up over here and come into the far side of the battery. In fact, let's double check that. I'm going to break the circuit there, and I'm going to do the following. I'm going to take a measurement here. And I get, let me get good contact on this. 6.68, it was saying, basically 6.7. 6.7 milliamp. Great. So the same amount that's coming out of the battery is the same amount coming into the battery. And it's not that it's flying through the circuit really quickly. I want to draw that back to what we had talked about before. The charges are already there. When I complete the circuit, all of the charges start moving. In fact, the charges move very, very slowly overall. I may make a subsequent video that actually shows some of the math on that. But it's kind of like playing musical chairs. Everyone moves together, but only when the music is on. Okay, I'm going to break this up. Oh, not break it apart there. Let's find out how much is going into the 1,000 ohm resistor. 0.65. So the current going in equals 0.65. Let me double check that real quick. Milliamp. Yep, 0.65 milliamp. Now one thing you'll notice is, hey, the green light's still on. Why? I've broken one part of the circuit, this branch, but there are 2 other branches that are still going. Now, if this were a regular light bulb, we would see it change depending on when I connect these. This is not a regular light bulb like you're used to, or the ones we experiment with. This one's a diode. You'll notice that it did just get noticeably darker, and that's because this is the main path that, in fact, we're about to see that, so I better not ruin the surprise. I'm going to connect this. We see it get brighter again. The current going through here is about 5.98. It's about 6.0. So our current through here is 6.0 milliamp. Now I'm going to point something out real quick. We have 6 milliamp going through this, and about 1/10 of that, 0.65, going through this. There's 10 times more current going through here. All right, here's what I'm going to do. It's dim, but it's still on because the other two branches are there. I'm going to reconnect this. Now we've got a lot more current going through. I'm going to check how much is going into the 5.1K, so the 5,100. We've got 0.13. 0.13 milliamp. Great. Now I'm going to check what's coming out of the 5,100 and going into the 100. 0.13. The same amount going in is the same amount coming back out and going into the next resistor. Because charges are not used up, they simply move through the circuit, carrying the energy. And to no one's great surprise, hopefully, 0.13 coming out over here, 0.13. That means that we've got 0.13 coming in here, we've got 6.0 coming in here, and we've got about 0.65 coming in here. If all of them are combining, then we'll have 6 plus 0.6, that'd be 6.78-ish, so we'd be looking at something like 6.78, maybe about 6.8, which we know should actually be the 6.7. Now remember, my meter is going to round this some. When we see 0.13 milliamp, I should probably drop it down some, and we'll see that it's much closer to 0.122 or something like that. So, to one significant figure, or even two significant figures, we can see that these are coming together. They split up here, some of them going this way, some of them going this way, and some of them going this way. Give me just a moment. I'm going to check on the camera. All right. Great. The camera was about to stop anyway, so glad I stopped to check it. Let's get our takeaway from this. The charges that come out of the battery, in fact, everything is moving together, so some charges start moving here, and the ones in front of them move, and the ones in front of them. Remember, think about this a lot like waiting in line. There are charges all throughout the circuit, so for this one to start moving, one over here has to move forward, and one over here. We're going to talk more about that, ways to imagine it, as we go through, but it's a lot like musical chairs. The only way charges can come out of the battery here is if a charge in front of them gets out of the way, and gets out of the way, gets out of the way, gets out of the way, and what happens is the moment a charge starts coming out of the battery here, one from this side is going back in. Everything is moving in unison. That's also why it does not matter which way or which sides you've got these components set up on. With one quick exception, not to undermine that, but with the resistor-based circuits that we're working with. This happy little character is a diode, and if you hook that one up backwards, then it will actually block the circuit and not let it go forward. There's some good upsides to that. Don't worry about diodes. The most that we'll do is possibly a project involving them, and I'll supplement with how they work. Now that being said, we've got a certain amount of current coming out here. It gets split at this. We call this a junction. Anywhere where the current can split and go in multiple ways. Now the big thing that I want to talk about, and I may have mentioned it before, many of you have learned the phrase, the path of least resistance, and you've learned that electricity will always go through the path of least resistance. One of the big things that you want to learn for this, in fact, I'm going to write this down so that you see it explicitly. Path of least resistance. Path of least resistance. Do yourself a favor. Forget this exists. Because you're almost guaranteed to draw the wrong conclusion. Let's look at what we've got here. I had a path. I had three paths, in fact. This one has a resistance of 1,000, this one has a resistance of 100, and this one has a resistance of 6,100. Now, if you go with just the idea of the path of least resistance, well, then that means all the charges are going to go down the middle one, because that's only 100. But we saw that they don't just go down the one, they actually go through all three of them. When we bring up the path of least resistance, what we're actually talking about is the majority of the current, the majority of the flow of charges. Now we can see that. This has a resistance of 100, and it had 6 milliamp, which was almost the total current. That being said, over here we had 1,000 resistance, and we had about 1/10 of that. In fact, this is 10 times easier to get through, 100 ohms versus 1,000 ohms. Since this is 10 times easier, 10 times the current will go through this one than it will through this one. But the electricity will go through any and all paths available if they can move through it. It's not just path of least resistance that they go, oh, that one's easiest, I'm going to go for that. They actually split up. Whatever has the least resistance will end up with the most current, but not all of the current. This one over here is 6,000 ohms is its resistance, and yet we still saw a little bit of the charges going that way. We had about 0.13 milliamp. Now, that's a very small amount compared to the total, but this is a lot more resistance than the other. But I want you to remember that the charges do not just go through the path of least resistance, they go through all of the paths, but more of it will go through the path that has the lower resistance. They'll actually balance themselves out. This one is 10 times harder to get through, so it gets 1/10 the current. This had about 6 milliamps. This has about 0.6 milliamps. 10 times easier, it gets 10 times the current. This is 60 times easier to get through than this. You take 6 milliamp and you divide it by 60, you're going to end up with about 0.1 milliamp. This is one thing that you want to keep an eye out for, and you're going to see as we go through that there are mathematical ways that these things have relationships. It's not simply that electricity is going to go through the path of least resistance. It's going to favor the path of least resistance, but it's going to split up the current based on the resistance in each of those paths. All right.